Alrighty, let's open up to page 417. We have one more graph to cover. We've been slowly developing and talking about our trig graphs. We've gone through sine, cosine, tangent, cosecant, secant, and I believe we have cotangent left. Is that correct? Yeah? Alright. So let's go ahead and try to fill out the table of values for cotangent, and then we'll plot some points to get the picture. Let's use the unit circle to help us out. In relation to the unit circle, how could we think about cotangent? In terms of x's or y's or sines and cosines, either one is fine. Yeah, Marie, go ahead. Cosine. There you go. Cosine over sine. Good. All right. So when we talk about our ordered pairs, we want to make sure we take the x-coordinate divided by the y-coordinate. So our 0 coordinate at the very beginning on the right-hand side, we have 1, 0. If we did x divided by y, what would our cotangent answer be? Yeah. Undefined. Most likely a vertical asymptote. All right, pi over 4, middle of the first quadrant, square root of 2 over 2, comma square root of 2 over 2. If we did x divided by y, yep, thanks Tori, we got 1. We're dividing the same number. Pi over 2 at the very top, x divided by y. 0. All right, 3 pi over 4, middle of the second quadrant. We're going to have the same ordered pair as the first quadrant. We just got to be careful what's positive, what's negative. Yeah, negative 1. All right, pi, very leftmost point. X divided by y, yeah. Undefined. 5 pi over 4, middle of the third quadrant. X divided by y. Yeah? 1. Good. They're both negative. All right. 3 pi over 2, very bottom. Yeah. 0. Good. 7 pi over 4, middle of the fourth quadrant. Marie, you're on a roll. Yeah? Negative 1. And then 2 pi back to where we started. Undefined vertical asymptote. All right, let's plot some of these points and characteristics. So at 0, we have a vertical asymptote. 3 pi over 4, we had 1, and then 0, and then negative 1. Asymptote at pi. All right, if you were to keep plotting, we would have another point at 1, and then 0, and then negative 1, and then another asymptote. Do you see how the pattern continues? Okay, so when we're going through the unit circle, it looks like we're graphing 2 cycles of cotangent because a pattern repeated itself twice. I know some of us are using pen, so I want to be careful. I only want you to draw in this first cycle, just because we're going to try to do some of the transformations at the bottom, and I don't want your graph to become too cluttered. Okay, but if you were to continue plotting points, you'd have the same exact shape, just written twice. Do we realize that? Can we see that based off the table? All right, let's go ahead and talk about period and amplitude of this original cotangent graph. What do you think, Marie? Go ahead. Just pi. Good. So that's the how wide a period is, the width, or the length, whatever word you want to use. What about amplitude? From the baseline or the middle? How far up or down you go? Yeah. It'd be infinity. Yep. Whenever you have maxes or mins or those vertices like we saw last week from those parabolas, you can count up to those points. But for tangent and cotangent, Notice how we can go up and down forever. So those are the infinity ones. Good job. All right, let's talk about some transformations. Maybe we wanted to stretch this graph in some capacity. What if we were going to multiply the cotangent function by 3? How would that change our cycle? What kind of transformation would we have? Yeah.
Vertical stretch.
There we go. Vertical stretch by 3. So we'll see how that affects the period or amplitude. All right, vertical stretch. We're going to make this curve go very, very tall. So if you were to vertically stretch a vertical asymptote, okay, that's still going to be there. You're stretching a vertical line even more vertical, so it's still a vertical line. So the asymptotes are going to stay where they are. The first dot on our cycle has a height of 1, so if we triple that, it's now up to 3. The middle dot has a height of 0, so if we triple 0, that's not going to go anywhere. And the bottom dot, height of -1, tripled would go down to -3. So if you try to connect the dots, we'd get that red graph. Notice how it's more linear because you're taking kind of a wavy, curly shape and you're stretching it vertically. It's going to become more straight.
Please excuse the interruption. All students taking the Keystone Biology, please report to your assigned room. And all students taking the Keystone Biology, so please report to your room. Thank you.
Good luck. All right, I kind of got ahead of myself and I forgot to ask you guys. When we graphed the original cycle, okay, the black one on the screen, did that shape look familiar? What did it kind of resemble? Yeah? Okay, so cubic kind of looks like this. Yeah, so it kind of resembles a flip almost of a cubic. That's good. Yeah, it kind of looks like a cubic graph. Did it look like another trig graph? Go, Tori. Tangent. Okay, so tangent, the one we graphed a few days ago, I'll graph it in blue. Okay. Tangent went kind of low to high when you read it from left to right, but notice how tangent goes high to low. It kind of has a little flip to it. They're opposite. I know. They're related to each other, so it makes sense that the graph should be very similar anyway. Yeah, they're flipped, just like tangent and cotangent are reciprocals or flips of each other. All right, let's take a look at our red graph. What is the period of the red graph, the amplitude of the red graph? Okay, the one that we stretched. Did anything change?
Also, we need Connor Holloway, Logan Jenner-Yuski, Savannah Yerk, and Vincent Vogel to report to the cafeteria. Thank you.
What about period or amplitude of our red graph? Yeah?
The period will still be high and amplitude will still be infinity.
The amplitude is still infinity. Okay, so notice how we didn't change how wide the cycle was. Okay, the asymptotes stay where they were, so the period's still pi. Technically, the amplitude did change, okay, because we had to take the original amplitude of infinity times 3, okay, because we're vertically stretching every point. But mathematically speaking, infinity times 3 is still infinity. It's still a very, very large number. So even though it doesn't look like it changed, okay, it physically did, and we can see that in the graph, how it became more straight. All right, let's try our next transformation. What about if we multiplied by a half on the inside? Yeah. There we go. All right, so we're going to make this curve shape get wider, not necessarily taller. So we'll see how that affects the period and amplitude. All right, so we're going to double all of the horizontal distances, meaning x values. The first asymptote we have has an x value of 0. If we double 0, that's not going to move. The first dot on the original black graph has an x value of pi over 4. If we double pi over 4, that's going to move to pi over 2. The middle dot had an x value of pi over 2. If we double pi over 2, that's going to move to pi. And the last dot was at 3 pi over 4. Double that would be 6 pi over 4, but that simplifies to 3 pi over 2. And then the last asymptote at pi, doubled would move to 2 pi. So we're going to play connect the dots, staying within those asymptotes. And notice how it gets more wavy because we're stretching it horizontally like an accordion. What about period and amplitude of our new blue one? Yeah. 2 pi, double the original, good. Amplitude. Yeah. Still infinity. Yep. Doing good? Haven't lost it? We spent a lot of time on this, which is good. All right, we're going to wrap up these graphs by filling in our last column for cotangent, or row for cotangent on page 411. Well, no, not quite. We still have two more sections to go over, so we're almost done. But this is the last for graphs, okay? So for cotangent, we did see some vertical asymptotes, so we'll try to list where those happened. Since we had vertical asymptotes, that means our domain is kind of restricted. We can be any number we want, but we cannot be the values of those asymptotes. We have to skip over those spots. So maybe we'll start with those. If you look on the original black graph, where were some of the asymptotes for cotangent? Good, Marie? Yeah? Uh-huh. And pi, yep. And it could go onto 2 pi. Yep, we saw that in the table, even though we didn't graph it. So that's just from 1 or 2 cycles, but notice how we could throw in dot, dot, dots depending on how many more cycles we wanted to do and in which direction. So with those numbers listed, we're going to try to figure out a rule that would give us the location of any vertical asymptote on a graph. You want to do it? Yeah.
Would it be 0 plus pi n?
Love it. How'd you get it? That's good.
So I picked a vertical asymptote 0, and
Okay.
then you see that the pattern is adding pi each time.
Yep.
So that's how I got pi, and is your variation to how many times you want to multiply pi.
Perfect. All right, so your first number, I don't care what you pick, is just have to be one of the asymptotes that you listed. Emily chose 0, which is perfectly fine. The pi n is the pattern between the terms, like what you have to add each time. So notice how that would just be a pi. So, and then the n represents how many times you want to go through a cycle, or how many cycles you want to have. Love it. All right. Period of cotangent. What did we list that as? The original black one that we graphed? Yeah? Pi. Good. All right. And range, we had amplitudes of infinity, right? So probably negative infinity to positive infinity. We can go up as far as we want and down as far as we want. All right, guys. Very, very good. We're going to switch gears today, and we're going to take a look at some algebraic properties of trig functions, not necessarily graphs like we've been focusing on the last few days. So I think some of us might like these last 2 sections maybe a little bit better. I know not all of us are graphing people. Some of us are because we like the visual, but others of us are very algebraic based. Okay, we like manipulating things. So I think we're going to have a good time with this section. So on page 419, we're going to talk about some trig identities. Okay, identities are basically true statements. We're going to use these true statements to help us rewrite or simplify or solve trig equations and expressions. So we're going to take something that looks fairly complicated, and we're going to use these identities to make it not so complicated. We're going to see how we can use them to help us with that. So there are several basic ones. These first 4 at the top, we're already familiar with these identities, but we're going to talk about the 3 bigger ones towards the bottom. So let's think about this. How can we rewrite tangent in terms of like trig functions that we already know? How is tangent related to x and y on the unit circle? Maybe we'll start that way. Yeah. Y over x. Okay, so if tangent is y over x, how else can we write tangent in terms of other trig functions? What do you think, Maddie? Cosine of theta. There we go. So whenever we see tangent, we can think about it as sine over cosine. We can rewrite it. Okay, this is an identity. This is a true statement. We can interchange those 2 values because they're equal. Almost like substitution. You know how when you plug in a number for x, okay, x and the number mean the same thing, so you can replace them. Those are identities. Those are true statements. What about cotangent? What do you think? Yeah.
X over y.
It'd be x over y on the unit circle. All right, so in terms of other trig functions, yeah?
1 over tangent.
You could think about it as 1 over tangent. Yep, it's the reciprocal of tangent. So if tangent is sine over cosine, what's the reciprocal? Yeah. Perfect. There we go. Cosine over sine. Okay, those are true statements. Those are interchangeable. What about secant? Good, Maddie? 1 over x. Okay, so in terms of a trig function, we'd have 1 over cosine. Good. All right, so those are interchangeable. And what about cosecant? Yeah?
1 over y.
1 over y. So this would be 1 over sine. Good. All right. We're familiar with those. We've already discussed those based off the unit circle, but usually in terms of x's and y's. But now we're going to get into the trig representations. They mean the same exact thing, though. All right, so these next 3 are a little bit different. Notice how it's just not tangent, secant, cotangent, secant. Now we have some type of an equation that we can use as an identity. And I would say this is the big one to know, okay, number 5. 6 and 7 are related to number 5. We'll see how that connection is brought up in a second. But what we're going to try to figure out is if we were to take cosine squared plus sine squared. Do you notice how those 2's or squareds are written in kind of a weird spot for us? I want you to think about this the same way as if we were to take a cosine value and square it. Okay. This is how you would have to type it in on your calculator, but mathematically we put the 2 after the cosine. The reason that is because if I were to write cosine of theta squared like that, some people might square the angle measurement, not necessarily all of the cosine function itself. So if this can be a little misconstrued, okay, a little confusing, we put the 2 after this trig function just to represent a squared value. Okay, but these mean the same thing. All right, let's think about this. What variable did cosine represent again on the unit circle? X, and sine was y. All right, so way back when we were talking about our unit circle kind of in the first quadrant, if we drew a few reference triangles in there to help us figure out those ordered pairs. Okay, it's been a while. But notice how if we put an x down here and a y right there, because we have an x distance and a y distance to get to that point, what's the hypotenuse if we're talking about the unit circle? Yeah? 1, okay. Is there an equation you can use to represent all of those sides in that triangle? Good, Rebecca? All right, the Pythagorean theorem, right? So that would look like x squared plus y squared equals 1 squared. But we know cosine is basically the same as x on the unit circle, and sine is the same thing as y on the unit circle. So instead of x squared plus y squared, we're simply using cosine squared plus sine squared. Do you see that relationship? It's a Pythagorean, it's called a Pythagorean identity because it comes from the Pythagorean theorem. Okay, Pythagorean identity. So what do you think this identity should equal? If this is x squared plus y squared equals, yeah, Rebecca? 1. Okay, 1 squared. Now, there are some manipulations of this that we might have to use when we go through some of our examples. So the basic one is cosine squared plus sine squared equals 1. But we'll go ahead and write down what some other ones might look like. And they're pretty simple, okay? It's nothing too difficult for us to imagine. If we were to subtract the cosine squared over, we would have sine squared theta equals 1 minus cosine squared. So there's one manipulation. Okay. Another one, instead of subtracting the cosine squared over, we could subtract the sine squared over. In that case, we'd have cosine squared equals 1 minus sine squared. What I'm trying to do is put all of the identities that we might have to utilize in these next two sections on this one page. That way it's kind of a go-to reference sheet. Okay, so this is kind of the main one, cosine squared plus sine squared equals 1. But notice how if you change some things, move some terms around, you could also get these identities. Okay, but they're related back to the main one. Okay, let's go ahead and check out the next one. 1 plus tangent squared plus secant squared. What if we were to take this main identity from number 5, okay, cosine squared plus sine squared equals 1, and we were to divide every single term by cosine squared? We know from algebra what you do to one, you do to all, right? Okay, so if we were to start with the main one from number 5 and divide everything by cosine squared, let's take a look at what would happen. What's cosine squared divided by cosine squared? Anything divided by itself is 1. Right? What about sine squared divided by cosine squared? Up here we said sine divided by cosine was simply tangent, but if we have sine squared divided by cosine squared, what do you think we're left with? Tangent squared, good. And what about 1 over cosine squared? We said 1 over cosine was simply secant, but 1 over cosine squared would lead us to secant squared. You see how that's what we started with for number 6. So we're taking the main Pythagorean identity from number 5 and simply dividing everything by cosine squared. What you do to one term, you do to all. Okay, very algebra concept there. All right, so that's where number 6 comes from. We can have some manipulations for this one as well. All right, so for instance, what if we subtracted 1 over to the other side? We could have tangent squared equals secant squared minus 1. Another manipulation, what if we subtracted tangent squared over? We'd have 1 equals secant squared minus tangent squared. Okay, those are other identities, but they're related back to the first one that we started with, which was essentially related to number 5. Okay, they're all connected, but they look different. It just depends on what algebraic step we did to get from one to the other. Whether we added or subtracted some things, whether we divided some things. Okay, it's really creepy because they're all connected somehow. Having that mind-blown moment. All right, let's try the next one. So 1 plus cotangent squared equals cosecant squared. Again, what if we were to start with the main Pythagorean identity from number 5, cosine squared plus sine squared equals 1. What do you think we're going to do for this one to make it look like number 7? Can you think about what we did at number 6? What do you think, Tori? Let's divide by sine squared. Good. All right. So cosine squared divided by sine squared. At the top we had cosine over sine was cotangent, but if both of these are being squared, that would leave us with cotangent squared. Sine squared divided by sine squared is 1. And 1 divided by sine squared, we would have cosecant squared. All right, notice how it matches number 7. These are just flipped. All right, but it's still the same identity. So let's talk about some manipulations of this one. What if we were to move some terms around? Let's say perhaps we subtracted cotangent squared over. We'd have 1 equals cosecant squared minus cotangent squared. And maybe the other one would be subtracting the 1 over. Okay, these are all of our identities. Okay, we have the 4 kind of easy ones at the top because we've talked about those before. We have the main one in number 5, okay, that Pythagorean identity, cosine squared plus sine squared equals 1. But the other ones that we have here are derivations of this number 5, where you can simply divide by cosine squared or sine squared to get the other ones. Okay, so these are all the identities that we're possibly going to use in the next 2 sections. So keep this page handy because we might have to reference it a few times. What we're going to try to do today is just a few examples of how we can use these identities to help us simplify complicated trig expressions. I don't know how many we'll actually get through, but we'll just see how many we can do. All right, so what we're going to try to do on the next page is rewrite each of the following in terms of sine or cosine and completely simplify them. We're going to try to use sine and cosine because I think those are the easier trig functions for us to use that we're more familiar with. And based off of those rewritten expressions, we're going to try to simplify to see what this craziness actually is in the end. Okay, we're going to go from like 3 or 4 trig functions possibly down to 1 or 2. Okay, we're going to try to simplify it. So let's see what we can do. Notice how we have a sine out front, so we don't really have to rewrite that. Okay, we're going to try to get things in terms of sine and cosine. How can we rewrite cosecant with a sine or a cosine in it? What do you think, Maddie? 1 over sine. Good. All right. If we look at the next term, that's cosine. We don't have to rewrite that one. And then we got to multiply tangent. How can we rewrite tangent in terms of sine or cosine? Sine over cosine, good. All right, notice how on your paper you have sines or cosines everywhere. Okay, it's no longer tangent, cosecant, anything like that. Now that we have all sines and cosines, we're going to use basic algebra to help us simplify. So what are some things that you notice might happen now that we have sines and cosines written there? What do you see, Rebecca? All right, so take a look on the right-hand side here. We have a cosine up top and a cosine on the bottom. Okay, they're being multiplied together, so that division would cancel out the multiplication, meaning the cosines are gone. I like it. So the only thing we're left with now is sine. Where do you guys want to go from there? What algebra steps do you want to try next? Go, Tori. We can do that. All right, if we distribute the sign in, we'll have sine squared, sine over sine. Okay, if we distribute it into the fraction. And if we distribute it into the other sign, sine times sine would be sine squared. All right. Can we keep going? Anything else going to simplify? What do you see?
It would be 1 minus sine squared theta.
There we go. Okay, sine divided by sine is 1. Now the question is, what is 1 minus sine squared? Yeah.
Okay, I don't know if this is probably not the answer you're going for.
Okay.
Does this have anything to do with the difference of squares? Where it's like 1, I know the 1 isn't squared.
Ooh, okay, so you could, here's the thing. All right, so you could factor this. This is a difference of squares. 1's a perfect square, sine's a perfect square. So maybe we'll write that over here, because we are going to talk about factoring in, probably tomorrow. You could rewrite this as 1 minus sine times 1 plus sine. Absolutely, that is a difference of squares. We might have to use that in other examples to help us simplify. Can we take the 1 minus sine squared, though, and rewrite it as something else? Can we use an identity on the front page? What do you think, Rebecca? Cosine squared. All right, so if we take a look at our identities, this was actually one of the manipulations from number 5. Notice how 1 minus sine squared is exactly the same as cosine squared. They're equal to each other, meaning we can replace them or substitute or interchange. So instead of that statement, we can simply write cosine squared. So notice how that complicated mess we started with, after using some identities and algebraic concepts, actually simplifies down to one term, which is a lot easier to work with. Okay, so we're basically going to be practicing this idea the next few days, okay, taking some complicated trig expressions and simplifying them down. It might not always just be one term. Sometimes you might have two, okay, but using those identities, maybe factoring in some instances like Tori saw, we could use those algebraic steps to help us out. Let's go ahead and try the next one. Let's get everything in terms of sine or cosine. All right, so the cosine out front can probably stay. Can we rewrite tangent? In terms of sine or cosine? Yeah. There we go. So if we're going to add cotangent, that would be cosine over sine. All right, I like that first step. Get everything in terms of sine and cosine. Where you go from here is basically up to you. What algebra steps do you want to use? We could try to add some fractions together. We could distribute in the cosine. I can't really tell you what's the right way or the wrong way because it's all up to what you see first or what you're more comfortable with. So where do we want to go from there? It's more like a personal preference. You have an idea, Marie? Go ahead. You want to distribute the cosine. All right, so if we distribute the cosine into the first term, notice how that cosine would cancel out with the cosine down below. So we're just going to be left with the sine that was in the numerator. However, if we distribute the cosine to the next fraction, that would be cosine squared over sine. I like it. Where do you want to go from there? Let's see, can we turn this sine into sine over 1 and possibly add those fractions together? How do you add fractions? Hey, Rebecca?
The common denominators, you can multiply the entire fraction
Uh-huh.
from sine.
All right, so we need to get the 1 and the sine to be exactly the same. To turn a 1 into a sine, we'd have to multiply it by sine. But if you multiply that down below, you have to multiply that up top. Okay, again, algebra work, what you do to one, you do to all in terms of a fraction. So, after getting a common denominator, we'll have sine squared over sine plus cosine squared over sine. Now that we have a common denominator, how do you actually add fractions? Good, Rebecca?
You just add the numerators and make the denominator.
There we go. Add the tops. So sine squared plus cosine squared. And then keep the common denominator. Do you notice anything? Can we use an identity to help us rewrite something? Do you see it? Yeah.
Would it just be sine of theta plus cosine squared?
Say it again.
Would it be just like, because of the two, like the sine squared and the sine of just theta, that would be sine 1 like to the first power?
Like you want to divide this out?
Yeah.
If these two things up top are being multiplied together, you could divide it out.
Oh.
But the fact that they're being added, the cancellation doesn't work that way. Okay? Do you see it, Tori?
The numerator becomes 1.
All right, the numerator becomes 1. Sine squared plus cosine squared is 1. That's our Pythagorean identity. Take a look at number 5. Okay, that's the main one, the big one. So whenever you see that, like cosine squared plus sine squared, I want a light bulb to be going off in your head. Like that's always going to be 1. That's the big one. All right, so we have 1 over sine. Can we rewrite that? What's 1 over sine? Yeah. Cosecant. There we go. That complicated mess we started with, after we rewrite it and use some identities in algebra, it's actually cosecant in the end. Craziness. Okay? We'll go through a bunch more tomorrow and the rest of the week, but from here on out, it's just algebraic manipulation and using those identities to help us simplify.